Hi, I'm Anand Bariya, and I'm going to cover a few topics in this physical design of ASICs class. Okay, so what is ASIC design? ASIC design, the acronym ASIC stands for Application Specific Integrated Circuits. What it actually means is integrated circuits that are designed for a very specific application, as opposed to integrated circuits that have that are very generic and can be used for various different applications. So a CPU, for example, is a generic device, and ASIC would be a device that say that you create a chip for driving a laser printer, for example. That would be an ASIC. So ASICs, the meaning of the term ASIC is IC that is designed for a specific, very narrow purpose. However, in this class, that's not the meaning that we're going to use for the term ASIC. For us, ASIC design represents a kind of design methodology. And in particular, what we mean by ASIC design is the design of logic circuits using pre-designed logic gates. Okay, this is the only way to design large logic circuits. And the important thing is that the logic circuits are designed using gates, not transistors. So in ASIC design, we rarely deal with PMOS and NMOS transistors that are the foundation of logic circuits. So we don't actually think in terms of transistors, we think in terms of gates. And in general, CMOS is the dominant technology in ASICs, but not the only one. The key aspect of ASIC design is that the design is with logic gates and not with transistors. What are some characteristics of ASICs? So ASICs are sequential circuits, and like all sequential circuits, they therefore have combinational and sequential gates. Combinational gates are gates like NAND gates, NOR gates, muxes, but they can be even more complex combinational gates in an ASIC. And sequential gates are flip-flops and latches, but for all intents and purposes, in an ASIC, there is only one type of sequential gate that's used very widely, and that's a D flip-flop. So it's very important that you know what a D flip-flop is. In fact, that's the one thing that you should immediately get familiar with, what a D flip-flop is, because that is we will use a lot of D flip-flop characteristics and functionality as we design ASICs. So ASICs are sequential circuits. ASICs are synchronous circuits, and as such, they have data signals and clock signals. The clock signals are what synchronizes the operation of an ASIC. And the way an ASIC is architected involves data flowing through combination logic, and then the output of combination logic is captured at D flip-flops at clock edges. In general, we use the word register to represent a collection of D flip-flops. So in an ASIC, you have registers and you have combination logic. And the output of combination logic is captured at registers. The input to combination logic is also driven by registers. So there are flops that launch data into combination logic, and the output of combination logic is captured by the flip-flops. What about analog circuits? Can you have analog circuitry in ASICs? So analog circuits may be integrated with the logic circuit in an ASIC. The design of the analog circuit does not fall under the banner of ASIC design. So in this class, we're not going to talk at all about any analog design or anything to do with analog circuitry. But it's important to keep in mind that analog circuits are quite commonly present in ASICs, but the ASIC design methodology involves just the integration of analog circuitry with the logic circuit. It does not, the design of analog circuit is a separate topic. So usually in ASICs, if analog circuits are present, they're provided pre-designed, and then the ASIC designer merely integrates the analog circuit with the rest of the digital logic. There are two parts of the ASIC design process. The front end part is where the actual design happens. So the front end of the ASIC design process involves the design of the logic itself, so logic design, then logic verification, where the designer checks if any bugs are in the design and fixes the bugs. So as the design is done, it is frequently verified to make sure that the design is on the right track. So logic design and logic verification are two of the critical steps of the front end part of the ASIC design process. And then there's also what is called timing constraint definition. So where the timing requirements of the logic are captured in some format. So logic design, logic verification, and development of timing constraints constitute the front end of the ASIC design process. The timing constraints, it may not be clear to you what they mean, but that will become clear during as this course progresses. For now, just note that the design of an ASIC involves the design of logic as well as formulation of the timing requirements. What type of clocks are there? What are the clock frequencies? What are the input and output delay requirements? Those constitute timing constraints. So these are the three primary aspects of front-end ASIC design. Once the logic is designed and verified and the timing constraints are defined, then the back-end of the ASIC design process commences. And this class is completely focused on the back-end, and the back-end largely comprises physical design. But there is also another aspect to the backend there's another aspect to chip design that we consider as part of the backend, which is test circuit insertion. So the backend of the ASIC design process involves, first of all, generating the logic netlist or the logic circuit itself, then inserting any logic for testing the chip, then physical design, which is creating the layout of the chip, and finally physical verification to make sure that the physical design is meeting all the foundry's design rules and that everything is correct on the layout. So that is a part of physical verification. So one thing you may wonder is, why is netlist generation in the backend, and is a netlist? First of all, what is netlist? I don't know if all of you know this term. A netlist is just another word for a circuit. So a logic circuit, we call it a netlist. Specifically, if a logic circuit is available, or if you have a logic circuit in the form of a text file, then that is called a netlist. If you have a logic circuit in the form of a graphic, then that is called a schematic. So you are probably familiar with logic circuits as schematics. So you'll have symbols for AND gates and NOR gates and so on, and you can draw those symbols and connect them. Then what you're doing is you're creating a schematic. However, that same circuit, if you describe in a text file, then we call that a netlist. So in the front end, we do logic design. That logic design step is designing by coding the behavior of the ASIC. And then when you have the behavior coded, you generate the actual logic circuit that implements that behavior. And that step, going from behavior to creating the logic circuit, is what we call netlist generation. And for the purposes of this class, I'm going to consider that step as being part of the backend of the ASIC design process. So although this class is not going to be on the front end of the ASIC design process, I'm just going to show you one slide just to set the context and give you an idea of what actually happens in the front end. And this is all that we're going to do as far as ASIC front end is concerned. Like I said, this class is very much focused on the back end. So how does an ASIC design even begin? So an ASIC design, as you would expect, begins with a document where a specification is written up. So the start of an ASIC of ASIC design is a design and architecture specification, and that would be essentially a PDF. So somebody has looked at a market and looked at an opportunity, let's say, and has come up with a specification for an ASIC and has written it up. And then somebody has looked at that requirement and created an architecture, has specified how this ASIC should be architected. So that design and architecture together comprises the starting specification of an ASIC. Once that document is there, then the actual ASIC design process can start. And so initially we are in the front end of the process. And the first step is design entry, where we manually code in Verilog the functionality that is specified in the design and architecture documents. So this is a manual step. The logic designers are actually writing code. And this code is written, this code is essentially captures the behavior of the ASIC. There's no actual design of the logic circuitry at this stage. And this has been one of the most critical developments in the history of chip design, where design can happen at the behavioral level rather than an actual structural level. Structural level meaning where you think in terms of gates. So today when ASICs are designed, the designer is not thinking in terms of gates. The designer is thinking in terms of behavior. And that is a much more, that eases the thought process considerably. And it in fact enables a designer to design very complex and large logic circuits, because they don't have to even think in terms of gates and connectivity. They just think in terms of behavior. So design entry involves behavioral coding, and the language that is commonly used for this coding is Verilog. So initially, you write some code and then you get behavioral Verilog. It is often referred to as RTL, and RTL stands for register transfer levels. On the left-hand side here, I have the Wikipedia definition of RTL. RTL models a synchronous digital circuit in terms of flow of data signals between registers and the logical operations performed on the signals. So as I had said in an earlier slide, an ASIC involves data flowing through combination logic and being captured in registers. And the data that enters the combination logic is also launched from registers. So basically, you can think of an ASIC as comprising registers that launch data into combination logic. The combination logic processes that data and generates some output, and that output is captured by registers. And so the way data is processed in an ASIC is it flows from registers to register through combination logic. And therefore, the behavioral coding in Verilog is also, the behavioral code also is done in a manner that is cognizant of this underlying architecture of an ASIC. So the way the behavior is coded is in terms of transfer of data from registers to registers. Okay, so registers are defined in the behavioral code, and then the combination, the behavior of the combination logic is coded, and the way that the behavioral code looks, it has data flowing from register to register, and therefore we call this behavioral code RTL, or register transfer logic, or register transfer level. So this is a very widely used term. And so at the end of the design entry step, you have some RTL, or behavioral Verilog. Initially, this RTL is unverified. Then we take it into a design verification step, which essentially involves simulating this RTL and see if the simulation gives us expected, if the behavior is as expected. If the simulations pass, then you have verified RTL, and then you can go to the backend. If the simulations fail, then you have to go back and fix the bugs in your Verilog code, behavioral code, resimulate, and keep doing that until everything passes, at which point you can start the actual implementation of the ASIC. In order to simulate, you have to have a test bench and test vector. So those are also coded in Verilog. And then separately, while this logic is being designed in Verilog, you also have timing constraints being coded up. And timing constraints essentially define what are the timing requirements of this circuit. What are the clocks in the circuit? What are the clock frequencies, and so on? All of that comprises timing constraints.